Hi guys, welcome back. So in this video, let's continue with the Bayes theorem. And Bayes theorem is a very fundamental theorem in probability. It's not fundamental, but it's very often used, and it's the basis behind the machine learning technique called naive Bayes. So in order to understand naive Bayes well, we need to understand Bayes theorem very, very well. So I'll explain what Bayes theorem is in this video with an example. So consider two events A and B, all right, from from a sample space that form a sample space, and let's say that we know from conditional probability that P of A and B is equal to P of A given B is equal to P of A and B upon P of B, right? Similarly, from conditional probability, we also know that P of B given A is equal to P of B and A upon P of A, right? If you don't know this, just look at the previous videos. I've covered this there. And from simple set theory over here, we know that P of A and B is equal to P of B and A, right? The intersection will be the same. P of A and B and A will be the same. So we can rearrange all these terms, and that gives us a formula, which is P of B given A is equal to P of A given B into P of B whole upon P of A. So why the Bayes theorem is so good, and what is the meaning behind this formula is that Bayes theorem helps us update the probability B, which is B, this one. It helps us update the probability B as we receive new data. Okay, so as we receive more or new information about the event A, we can keep updating our probability B. Okay, so we can update the belief about an event as and when new data comes in. In this case, the new data should be about the event A. So as and when that comes in, we can update the probability B. And now I'll give a very good example of Bayes theorem, and we'll try to solve the Monty Hall problem using Bayes theorem. Okay, before we move on to the Monty Hall problem, let me just give you some terminologies here about what all of these terms are. Okay, so I'll write it here. We have P of P, right, in the formula over here, P of B, this one. P of B is the prior probability. Okay, this is called the prior probability. Prior prob. So what this does is it just gives us the estimate of the probability without any additional information. Okay. P of B given A is called the posterior, right? So this is so given that the event A has occurred, what is the probability of the occurrence of B? That is post the additional information that A has occurred. What is the estimated probability of the occurrence of B? That is what posterior probability is. Okay, and now P of A given B over here, P of A given B is called the likelihood of observing A given the evidence B. Likelihood. And again, the denominator, P of A over here, is called the prior probability of A. Okay, sorry. This is the prior probability of A. Okay, this here is the prior probability of B, right? So now that we know the terminology, let's go on to solving the Monty Hall problem. Okay, so now let's look at the Monty Hall problem. So the Monty Hall problem is a very popular problem. There was this game show where the host of the show, his name was Monty Hall, I believe. So the idea behind that game show was there are three doors, okay? Door one, door two, and door three. And there is a prize behind one of these doors. And behind the other two doors, there's no prize. Okay. Let's say the prize is a car, okay, and the doors that don't have a prize behind them have a goat behind them. So the contestant on the show is asked to select a door, and no matter what door he selects, the door can have a prize behind it or it cannot have a prize behind it. No matter what door the contestant selects, Monty will go on to open a door that has a goat behind it. Okay? And then he will ask you to choose again. Do you still want to use the door? Or do you still want to open the door that you chose? Or do you want to switch? Do you want to switch to the other door? So in this example, let's say that door 1 has the prize behind it, which is the car, and door 2 and 3 have a goat behind them. Okay? And the contestant is asked to choose what door he wants to select. So let's say the contestant chose door 1. Okay? And Monty opens door 2 to just update the belief of the contestant that there is nothing behind door 2, right? Door 2 has goat behind it. So now, according to Bayes' theorem, should you still go mathematically? This is just mathematical. Should you choose the same door and go on to open the same door, or or should you switch? All right, that's this has been the question behind the Monty Hall problem. In fact, when this problem came out in the magazine, I think back in 1988, like there was a big commotion behind this problem. People were just there were PhDs and master's students and mathematicians who tried to solve this problem. And it's actually pretty simple if you use the Bayes theorem. Mathematically, the Bayes theorem would go on like this. Okay, so let C1, C2, and C3. Let C1, C2, and C3 be the events that the prize, which is a car, is behind door 1, 2, and 3 respectively. Okay, let D1, D2, and D3, D2, and D3 be the events that Monty opens door 1, 2, and 3 respectively. So we know that the prior probability C1, C2, C3 is 1 by 3, right? So the prior probability, the normal probability that the car is behind door C1 or C2 or C3 is 1 by 3 because it can be behind any one of them. So now let's assume that the player chose door 1. Okay, the player chooses door 1 and Monty opens door 2 to reveal a goat. Door 1 has a car behind it, but Monty opens door 2 to reveal a goat. Now we would like to calculate the posterior probability, which is, so this is the door that player chooses. Player choose. Okay, so we want to calculate the posterior probability P of C1 given D2. Okay, that is the probability that the car is behind door 1, the door which is initially chosen by a player, when Monty has provided the additional information that there is a goat behind the door D2. Okay, C1 is the prior probability of a car being behind any one of them, and Monty opens door 2 to show that there is no car behind it. So we want to find the probability that we want to find the probability P of C1 given D2, that the car is behind C1, given that Monty has opened D2. So we can, using Bayes theorem, we can write this as follows. P of D2 given C1 into P of C1 whole upon P of D2, right? Now, what is P of D2 given C1? Probability of D2 given C1. This basically says that what is the probability that Monty will open door 2 given that the contestant has chosen door C1, right? So this is equal to half, correct? Because if contestant has chosen the door C1, according to the rules of the game, Monty will open either door 2 or door 3. So he can choose door 2 or door 3. It doesn't matter. The probability that Monty will open door 2, given that the contestant has chosen C1, is 1 by 2. Okay. Probability of C1, which is this. This is just 1 by 3. We know this from the prior probability over here. Okay. And probability of D2. What is D2? D2 is basically so D1, D2, D3 is basically the events that Monty opens door 1 or 2, door 1, 2, 3 respectively, okay? So what is the probability of D2? This is half again because Monty is going to open either D1 or D2 or D3. Sorry, not D1. He's going to open D2 or D3. He's not going to open D1 because the contestant has chosen D1, right? And there's a price behind it. So he won't open the door that has a price behind it. So this is basically how you do it. So this is equal to, let me just move this. This is equal to 1 by 3 into 1 by 2 whole upon 1 by 2. So probability of C1 given D2 is equal to 1 by 3 into 1 by 2 minus 1, divide by 1 by 2. Okay. Now we know that probability of C2 given D2 is equal to 0, right? Because if the contestant chooses the door C2, Monty is not going to open the door D2, right? So what is the probability that what is the probability that there's a prize behind C3 and Monty opens D2, right? This is just equal to 1 minus P of C1 given D2. This is equivalent to A complement equals 1 minus A from set theory. So this is equal to 1 minus 1 by 3 into 1 by 2 whole upon 1 by 2, which is equal to 2 by 3. So this actually shows that by probability and by the rules of probability, the contestant is better off choosing the other door and not sticking to the door that he has chosen right now. Because according to probability, that there's a higher probability that there's a car behind the other door, right? Now, obviously, in this case, we knew that the car is behind door 1 and not door 3, but the mathematics tells you the to choose door 3, which is to switch to your door, which is to switch your door from door 1 to door 3. See, this is the essence of mathematics. What actually seems intuitive will not be mathematically correct. If you ask this problem to a lot of people, they will say that I will stick to this door, but the mathematic tells you that it's more profitable, or in the long run you will win if you choose the other door. This is what Bayes' theorem is all about. And I really like the Monty Hall problem. It's incredibly cool.